machine. Spray it at a colder processing set point. Wood, concrete, plastics, gravel, rock, and metal. Again, when we are processing material, it will take time and experience for us to be able to start the day and say, all right, you know what, I'm spraying on gravel today, we're doing a slab, under slab, it's cold, it's a heat sink, I need to spray at 130. You'll learn as time goes on, as you're paying attention to this stuff, you'll get closer to a start point. If I'm going on a wood substrate, I may know after time I need to start at like 120, right? But if you're not paying attention and you're not making these adjustments, you may never learn that foam's, personality, so to speak, on every single substrate. Also, the thickness and what you're trying to spray, your reactivity needs to be adjusted. If I go from spraying closed cell in a 1 inch or 1.5 inch lift, and then I've got a wall where I've got to spray 4 inches of closed cell or 3 inches of closed cell, I can't just go from 1 inch lifts to a 3 inch lifts and expect the foam to perform at its best if I don't adjust the machine. So it is important that if you're spraying a section, let's say I'm spraying an exterior wall that's 500 square feet and I'm doing a 2 inch lift, but I know that this back wall is getting 4 inches of closed cell. Before I get finished with this wall, I'm gonna go have my guy bring me down 10 degrees, whatever it is, so that way when I'm done, my hose is cooled off and now I've made an adjustment for this wall for a 4 inch lift. All right, make sense? Lift thicknesses. Every formulation will have limitations on lift thickness. Different spray thicknesses will have temperatures in which they will perform their best. Spraying over foam versus the original substrate. Thick lifts can run a risk of thermal degradation and elongated cells. A couple years ago, the industry started introducing what was called high lift closed cell, and before that, we were limited to 2 inches. So we had these guys that were used to spraying 2 inch lifts, getting the foam to perform and sound, and everything was used to a 2 inch lift. Then we went to these super high inch lifts. If you're spraying a high inch lift, you have your reactivity profile where you have your end of rise or the gel time. You have to be very mindful as that foam is rising. If you're introducing a high pressure droplet into that foam as it's reaching the end of its rise, you're injecting cells that are going to tear apart and they're going to create these really long cell structures. All right. A cell structure is a bubble that holds onto a gas in closed cells. That bubble is going to experience pressure changes due to temperature. The whole idea is that cell needs to be strong enough to hold its shape while the gas inside of it wants to contract or expand due to temperatures. Well, if that cell is weak and elongated, right, we spray this job in the summertime, it might be fine. Come wintertime when it cools off, the gases inside that cell structure, there's this thing called a strut wall assembly. A strut wall assembly is where the sample is cut and you see all the cells interacting with each other and they need to be stacked in a uniform way. That's what creates the compression strength that we need. If those cells are elongated, well, they may be strong on their end, but when the compression comes from the sides, they collapse, okay? So if we're spraying a thick lift at too high of a temperature, our pass is into foam that is reaching the end of its rise profile. We're encapsulating these extremely elongated cell structures. We will have failure. It's not a matter of if, it's not a matter of if, it's a matter of when. So you may be fine. You sprayed this job in the summertime, the gases in the cell structures are wanting to expand, everything is keeping itself intact. Homeowners move in, sheetrock's up, Christmas ornaments are in, and all of a sudden they start hearing popping and cracking in their attic. Well, that cell structure that was in that sample has cooled off, and when one cell collapses, 4 collapse, and then 16 collapse. And the next thing you know, you've got complete cellular collapse on the entire sample set of foam, and you've got pulling away from studs, delaminating off the substrate. And it was all due to taking that foam beyond its ability to maintain its shape. That's all it is. It's a bunch of cells, a bunch of bubbles. We have to make those bubbles as round as possible. Spraying too hot, spraying too thick is the problem. Now, with these high lift foams, they're testing for exothermic reaction. Yeah, we can spray a 6-inch sample of foam and it won't get hot enough to combust, but they're not talking about how to spray to achieve a 6-inch lift. You can't spray 4 inches like you would spray 2 inches where you're riding the wave. You still can, but you need to drop your temperatures, delay the reaction time, slow down the reaction profile so you can stay ahead of it just enough to where your pattern isn't into that foam that's reaching the end of its rise. Once that foam gets injected, it needs enough time to recover. So when your pattern is away from it, it's still growing and it can heal itself. And those bubbles can come back to a circle, to a sphere. That's what we have to be mindful of. Our number one failure in closed cell is cellular degradation. Not thermal degradation, cellular degradation. And that's because we're tearing these cells apart. And unfortunately, with this new movement of really pretty cosmetic closed cell, where foams are really, really flat, we run a risk of injecting foam and making it flat, because that's what we're doing. We're beating the foam back flat as we're spraying. It looks great, but we have to be careful because we're tearing these cell structures apart. All right? Just remember, we want bubbles, not elongated cells. All right, the examples of reactivity. So as you can see, we're spraying on gravel, we're spraying on a nice insulated piece of fabric mesh. If you notice on the purple guy though, you notice there's no liquid line, there's no what's called cream time. His pattern is spraying on foam that has already kicked and is trying to expand. He is destroying that foam as it's expanding and beating it flat, creating elongated cell structures. And every foam is different, but if you look over here to the guy spraying that metal building, you notice that 50% or more of his pass is in that brown line. The brown line is where you really need to try to achieve your thickness. The thicker the liquid, the thicker the foam, right? It may be a little bit more difficult to get it flat, but that foam is going to perform better than the foam in the purple that's being sprayed flat. Because his foam, if it experiences extreme temperature changes from hot to cold, it's going to collapse. It's going to create so much negative pressure. I've seen it break 2x4s because the adhesion was so great, but the cellular collapse exceeded the adhesion, the adhesion exceeded the cellular pressure that it broke the 2x4s. So really and truly, this guy over here on the metal building, he's more dialed in than this guy spraying this purple foam. That's what we're looking for. And every manufacturer is going to have what's either called an initiation time or cream time. That number that we give you is very, very important. Some of them are half a second, some of them are 2 seconds. That foam may be spraying differently. This foam may be either too hot or that's what they want it to do. Maybe that's a 2-inch foam and that'll work. If you spray too hot, this is what happens. The foam cells got so big, so fast, and they expanded to where the strut wall was thin, and it didn't have the support to hold its shape as that hot gas contracts. Yes, sir?
In some of these metal buildings you get in and there, the metal can be upwards of 120, 130 degrees that you're spraying on.
Yep.
What's your recommendation in that case? Because you can turn your temperature down to where you're shooting stream and it can still hit that metal and be.
So when you drop your temperatures that much, what happened? What happened to the mix? Your energy fell to shit in the chamber, right? If you don't have a good pattern, if you've got a clean chamber and you don't have pattern development, picture a candy cane, that swirl. That's what's happening in your chamber. The material doesn't want to mix to begin with. So if you're shooting a stream or a poor pattern, I can already tell you don't have mix, right? So in those circumstances, you have to make a judgment call. Spray the roof first thing in the morning. Get it done. And if it gets too hot, drop down and start spraying walls. You may not be able to spray that entire zone in a day. That's a judgment call that you have to make. I have had people put fans on roof decks and it just never gets cool. There will be circumstances where there's nothing you can do except for spray at night. I would rather spray at night and have my guys bitch and complain, but give them the next day off, than spray that roof deck and come back in 2 years because it's fallen off and it's on the floor. Or what happens is that foam puts so much stress on that metal building that you ripple the metal, you bend framing, you start to degrade the building as a whole. Me as a homeowner, if you just come to me and say, sir, we're experiencing extremely high heats, we can do some of this job, but we're gonna have to come back in the evening to do this. Otherwise, I'm not gonna be able to do the job. That's where it comes down to, first off, the guy on the gun. If you're not an owner operator and you're an applicator, you have to have enough confidence and understanding. You have to understand what you're trying to communicate. Because if you just say, boss, it's too hot, well, he might not understand. It's our job to say, sir, foam's too hot, it's reacting too fast, it's gonna have cellular degradation, it's gonna shrink, it's gonna fall. Or, let's come back tonight. Let's let it cool off, let's get some fans on this building, and I can knock this out in 2 or 3 hours. Just communicate to the homeowner. If you're an owner operator, you don't want a homeowner coming back to you saying, dude, what happened? Why didn't we do this to begin with? Communication is one of your ways to fix this. But yeah, so down here in Florida, there are days where we can't spray. It happens. And I would rather take a day off and have a homeowner a little bit upset with me than be extremely upset with me because I sprayed a foam that failed. Right? And unfortunately, the guys like up in the Northeast or even north of the Mason-Dixon line, there's more jobs in the summer, right? So you're spraying all these summer jobs. They want to move in by Christmas. They want to be in their home for the holidays. Well, that foam that was sprayed too hot, the cell structures are complete trash, potentially. Now it starts to cool off, that roof deck gets cold, that foam shrinks because the foam doesn't necessarily shrink, the gas wants to contract. If the strut assembly, the cells all together are strong enough to hold that negative pressure out, you won't have a problem. But if those cell structures are compromised, either from contamination of open cell or over lift thicknesses, it's going to contract and it's going to pop, and now you're going to have a bigger problem. Now you've got remediation in a home where people are living. It's not a good scenario. All right.
We always say work with the sun. Maybe when it's too hot, you can work in the shade.
That's exactly right.
Get some things done.
100%. Yeah, like in the summertime, it would be better to start in the hot zone anyways and finish in the cooler sections. And this is what we're talking about, north side versus south side, roof line versus walls, basements, crawl spaces, mornings. If you have the ability to work with the environment to your benefit, start in the roof deck, get as much done as you can. When it gets too hot, drop down to the north side of the wall or the south side of the building in the morning, do the crawl space. But you know these things by taking temperature readings throughout the day, find out what the substrate temperatures are, and work with that to your advantage. Being mindful, we also need to make adjustments in the machine, all right? Impacts on reactivity. Processing temperatures, pressures need to be considered when changing gun configuration, such as chamber size, flat tip, extension tip. Distance between the gun and the substrate can affect initiation due to heat loss. Stroke length while spraying. So you see the guy on the right, he's spraying in a 16-inch wall cavity. You see a nice reactivity, a nice wet line. You see the guy on the wall or on the floor, again, nice wet line. He's in a really good section there. If you were to flip those configurations, the guy on the right might be too fast. That foam would be so fast that by the time he comes back across it, it's starting to react. Your reaction, your wet line, needs to be at least 1 stroke length. If it's chasing you, that means when you come back across it, that foam that you started with is reaching its end of rise profile. Be mindful, you want that wet line, okay? Failure. Spray foam outside of the target parameters can have a negative effect on the finished product. Sprayed too hot, the foam can lock up. So worst case scenario, you spray close cell too hot, it will lock up before it's reached its full potential. So you can easily take a 2-pound foam and make it a 3-pound foam by spraying it too hot. Because you're on the clock. When you mix those two chemicals together and there's heat involved, that catalyst is kicking off, and that foam may only get halfway through its rise and lock up. Now it's a very strong foam, but you might only get half the yield that you needed because you sprayed too hot. Spray too cold and the foam will have poor pattern development, sag, drip, become friable, delaminate, or pocket. Cold processed foam will also have a higher chance to retain odor over a long period of time. Cold foam stinks, hot foam shrinks, okay? So if you've got foam that is being sprayed cold, you're gonna have all kinds of problems as far as odor, because when you create a polyurethane by mixing A side and B side components, that material has to hit a certain temperature for what's called cross-linking to happen. It needs a certain temperature for everything to bond. If it gets stalled out and you never hit that temperature, you're gonna have a very high chance of odor. So if you're in a crawl space and your foam is super runny, don't keep spraying. Stop, remove that. Wait for your hose to heat up, respray it. Low dynamic pressure and the foam will not reach efficient mix. Pattern development will suffer. The material may not mix enough to react out all the components, causing the highest chances of odor, delamination, poor cell structure, and resulting in a number of failures that could surface after the install is complete. Here are some examples. So we have low temperature poor mix. Right here, this is off ratio cold poor mix, one or the other. Right here we have cellular and temperature degradation. This foam was sprayed too hot, too thick. The cell structures, you see these little bubble cells? These are the cells that are going to be compromised when the temperatures drop and the foam cools off. And when one cell falls, the entire strut assembly starts to collapse. Also with temperature thermal degradation, you're going to have a very unpleasant odor. And even if you were to spray over this with good foam, that foam odor will come out. You do not bury foam that is questionable. I've been on many houses where a 2-foot section of foam was sprayed off ratio or cold. It ruined the entire experience in the home. The entire home had to be removed because we couldn't guarantee that that was the only section that was sprayed that way. This right here it's not really a good explanation, but if you were to see these dripping marks like this, that's an indication of cold foam. If I get an odor complaint from a homeowner and I go in the attic and I see a lot of this, I can tell you probably have unfinished foam that's gonna stink, and it's all gonna have to come out. Now also you'll see this in some areas where you just put too much too fast, but if the entire attic looks like that, we have bigger problems. This foam right here could have been sprayed nicely during the summertime, but maybe too thick of a lift on that outside edge, and the cells just couldn't take it. This could also be off ratio, but since it's only isolated to one little area right here, he probably did a couple touch-ups too fast back to back and just overheated the foam. In this area here, we've just got all kinds of stuff going on. This looks like he had no hose heat. Both of these actually, he probably had no hose heat, which caused off ratio scenario as well as poor impingement energy, creating bad mix, poor efficiency. All right, same thing here. See how every other cell is fine? This could have been a check valve or intermittent issues, or I think he was outrunning his primary heaters, and this foam was the hot material that was in the hose, and it got cold and a cold slug came through, where the material was not leaving the machine at the proper temperatures. By the time that cold slug got to the gun, a brief imbalance in pressure because the viscosity of the B side was too high, and caused this. This is an odor complaint as well as a delamination complaint. Down here, if you see these little strings on the back side of open cell, that's cold. Your foam was too cold, all right? And or there was moisture present. Poor pattern development, more than likely cold hose. There's a crack right here underneath this yellow line. That foam was sprayed too thick, and the cell structure, as it was creating heat, because close-up will continue to create heat for minutes. The thicker, it can continue to climb for 10 minutes. Well, within that 10 minutes, the cell structure has set. But if the gas inside is still getting hot, it continues to want to expand. Some people call this bread loafing, which is like a secondary lift. And the cell structure no longer has elasticity, and it will crack, okay? Typically when you see stuff like that, that's because they sprayed it too thick. Open cell with a void on the backside with skin. That skin is called onion skin with a backside void. Temperatures were too cold for that substrate, or the substrate was too cold for that processing temperature of that material. Do you have any questions? Yes, sir.
I see a lot of videos of people spraying closed cell with long strokes up and down. Are you better off staying side to side so you can stay in that wet line, or?
So better has a wide range of things that it could be. You can vertically spray with long cycles as long as when you come back across on your second and third stroke, your pattern is not into foam that is reaching the end of its rise. You can spray vertically in a 36-inch lift, but typically you're gonna run a little bit cooler temperatures. You're probably gonna have a little bit larger of a chamber because your pattern being circular, you want it on the edge of that rise, but not onto the foam that's reaching the end of the rise. Now, when you say better, if it was me and I'm being safe, I'm trying to limit liability, I'm trying to increase as much yield as possible, but cosmetics aren't necessarily what I'm looking for. I'm gonna spray side to side, it's gonna be a little bit more texture to it, and then I'll go over that with a vertical spray touch-up to flatten it out. So a really good production guy would spray the majority of his lift side to side, short strokes, back off, do a half-inch touch-up to really flatten it out. There's a couple of ways to do it better. But yeah, you can definitely spray it vertical, you just have to know what you're looking for. Typically, if you're dialed in for spraying a 36-inch vertical lift, you're not gonna be dialed in for spraying side to side and vice versa. So you just gotta be mindful. That answer your question?
How do you stop the so-called butter movement? It's not always good for them.
Unfortunately, it's not necessarily, okay, so there's this thing where flat foam has more uniform thickness, right? So you could argue that, yeah, your yield is lower, but your inconsistencies are less, so you can technically not overspray as easily. I think that a perfect job would be a rough install at first, and then a touch-up coat on top. So you've got nice warm substrate, you've got a thicker lift, your install yield is gonna be better, and flash it, it's called cross-hatching. So whatever you spray first, your second coat is the opposite direction, and it flattens it out. But unfortunately, I think until we realize that this butter movement is increasing our liability, it's gonna be here. Yeah. Unfortunately, it's insulation. As long as the R value is there, I do think that bumpy foam sprayed at a better rate is a more uniform cell structure, right? The cells are not gonna be damaged. So maybe it's better. But we have set the standard, unfortunately, that people want this flat, uniform foam. And I'm not necessarily hating on it, because I like pretty foam too. But there's a time and place. And if it's in a wall, I want to limit liability. This is going to be a homeowner that lives in this with their family. I know that if I spray it really, really flat, I'm increasing my chances of destroying the cell structure. I'm going to spray side to side, stay away from the rise, and come back over it with a flash coat and flatten it out. And get my uniform thickness. Absolutely. My thing with circles is you're increasing the chance that it's into that foam that's reaching the end of its rise. You have to be in tune with your equipment to figure out what you need. So yeah, there's not necessarily one way to do it. Any other questions? Yes, sir.
You didn't mention about actually the raw materials, the temperatures of those, which, obviously you want to keep those close to where they need to be before you can spray them, because if you let them get too cold, right, your proportioner can only heat it so much.
Well, correct. Delta T, right? So you want to make sure that your machine has the capacity to bring your material from the drums through the machine, to the machine. So if your viscosities are too thick because your drum temperatures are low, you won't feed the machine. And the material leaving the machine at that flow rate needs to reach a target temperature. Yeah, so your drums on the rig need to be within a certain temperature to be able to maintain your target, right? So you may have a 70-degree drum, but if your high flow rate for the day, like with a 5252 at 1500 PSI, your delta T may only be 30, 40 degrees. Again, this goes back to you need to watch your machine while someone's spraying. Typical cavity from top to bottom on an 8-foot wall is 22 seconds. Do a 22-second trigger pull and see if you outrun your heaters. If you outrun your heaters by 10 degrees, you have two things you can do. Slow the flow rate by dropping your chamber size, or better yet, increasing your drum temperatures 10 degrees. With closed cell, you may not have that option, So you slow the flow rate, drop your chamber size, allow that material to go through the heaters at a slower rate, get it up to target. But it boils down, watch your machine. That's what it comes down to. But yes, thank you, appreciate that. Anything else?
So if I'm doing a split pass where I'm spraying 2 inches and coming back with another inch, like 15 minutes later, should I expect to run it at temperature?
So,
Spray it to cold versus to wood substrate?
well, so you're spraying it a thinner lift, which needs additional heat anyways. So you would be better off spraying at a thinner lift at the same temperature. If you were to spray a thin temperature on that original substrate, you probably wouldn't be able to. But now that you're on warm foam, you've got a head start. Now, you can do too much. Like if you do 2 inches plus another 2 inches, obviously that's a problem, right? So what I tell people to do, your recoat time needs to be within 10 degrees of ambient. So if it's 90 degrees in your house, you spray 2 inches of foam. When that foam gets to 100 degrees, you can go right back over it.
And are you talking surface temperature or internal?
Surface temperature.
Surface.
Yeah, we're looking for 90 degrees or ambient. That's kind of what we're looking for. And at 100 degrees, you're within that 10 degree window, you go right back over it. Yeah. I've never been a big component of time. Like where they say, first coat, give it 30 minutes, and go back over it. We go for 90 or ambient, whichever's the closest. If you're in a 120 degree attic, you're never going to get to 90, right? So we're looking for 120 degrees on the foam. So, yeah. But yeah, you can actually, you need to pay attention to that stuff. Anything else? That's it. That's a wrap.
Thank you.
Opportunity to work across the country with a lot of guys, and some young ladies that are also fantastic. And I think what I have to offer is the knowledge that I've gained over the broad spectrum, whether it be environmental, rig configurations, personalities, building requirements. And I think I can deliver it to a certain point in a message that allows people to get a bigger grasp on what it is we do on a daily basis. So, let's see here. So one of the things that we do is we're a mobile manufacturer. The chemical I work for, we make the material, we put it in a drum, but it's you at the gun, at the end of the day, that's a mobile manufacturer that's installing a finished product. And with that being a mobile manufacturing facility, we experience variables every day, all day, whether it be pressures, temperatures, humidity, dew point, substrate type, distance from substrate to gun, elevation, you name it, we experience it. So one of the things that I am focusing on today is taking a product and being able to understand what that product is going through and what it does for its reaction. So the material starts at the drum, goes to the machine, gets heated, gets pressurized, travels through the heated hose, gets delivered to a gun where it's dispensed into an atomized pattern, goes through the air and hits a substrate. There's a lot of influence on that finished product, things that can affect reactivity. Every manufacturer has multiple formulations, and every formulation has different reactivity profiles. And during the pandemic, I think we've been exposed to products that are maybe unfamiliar to us because that's what we had access to. Maybe we've been spraying a certain product for years. We start to spray a new product, and its processing parameters and reactivity are completely different. Now, a lot of times what I've found is an applicator gets a foam that he's familiar with, he dials it in, he knows what it looks like, what it sounds like when it's on its peak performance. Another manufacturer may have a peak performance with a different reactivity. Maybe it's a little slower, maybe it's a little faster, maybe its lift thicknesses are a little bit different. So in today's lecture, what we're going to be talking about is making changes. Things change throughout the day. And you may be familiar with your product, but we may not understand that elevation affects reactivity. Dew point, humidity, air temperature, substrate temperature, things change throughout the day that foam needs to change with. If I have a manufactured product that has been sprayed at the same pressures and temperatures for the entire day, you're going to have different finished products throughout that building. And the reason being is humidity, increasing humidity allows that material to lose temperature faster as it travels through the air. It can pick up residual moisture and add it to the reaction of the finished product. And some of the terms that you'll hear is cream time, gel time, tack-free time, and end of rise. When a material is being manufactured in a facility, they do what's called a cup test. And that cup test is where they blend the material in 77 degrees room temperature. They blend it extremely fast, and they document where it goes from a liquid to a foam, end of foam, or it'll start to a foam rise. It'll have a gel or a string time, and then it has its tack-free time and end of rise. All of these things are tested, and they have to be within a bracket. So there's allowable tolerances for each of these reactions. And the reason we do that is when we blend a product in our facility, we want to make sure that there's consistency from batch to batch, okay? So if you're out in the field, you need to do the same thing. You know, you're not changing chemistry, but you're changing influence. And the influence can change initiation, which is your cream time. It can affect all of these things. If I set my machine to spray on a 75-degree day and it's perfect, and all of a sudden a storm front rolls in and a fog bank comes in, you've got dew point and humidity to worry about. You may have to change either your distance from the substrate, pattern size, output, temperatures, something to compensate for that influence from the additional humidity. Temperatures down here in the south, it could be 45 degrees in the morning and 95 by mid-afternoon. If I'm not changing my processing parameters, the foam's not going to be the same. All right? And I know a lot of people think that, you know, you're spraying foam, it's not necessarily drippy, it's spraying okay, but you can spray a foam that looks and presents good, that may have bad cell structure. It didn't get enough heat to finish out and it's friable. You have delamination and pocketing on the back of the material between the substrate and the foam. If you don't know that good foam can also be bad foam, you may not understand how much of an influence processing can have. So don't think that just because it looks good and I've been spraying it this way for multiple years, doesn't mean that you're reaching the peak performance of that foam. You can affect yield, overall quality, you can increase risk, odor issues, delamination, you name it. All right, formulation changes. Every product has a certain formulation, especially closed cell. You can have winter versus summer blend. The processing temperatures may be similar, but the window, the bracket in which those temperatures are will be different. A rough example, winter foams can be good down from 25 to 45 or 25 to 65, and your summer blend could be good from 45 to 105. You just need to pay attention and read what manufacturers are recommending for those products. Open cell versus closed cell. Some may be a 30-degree different within the same manufacturer. So there's a couple manufacturers out there that have different types of closed cell or different types of open cell. One of those formulations may have a 20, 30, 40-degree different bracket that you need to be aware of. So if you spray one product and it may be the same manufacturer, you need to document and track which formulation that is, right? Because it could alter everything. I know during the pandemic, everybody was a little short on material, or they were put in a bind where they had to have access to multiple manufacturers, which is fine. But I think what needs to happen is when you're going from manufacturer to manufacturer, change-out procedures need to be done correctly, but your processing and your influence on that needs to be adjusted. That's why I recommend getting a tech on site, somebody that's familiar with that specific brand, and allow them to teach you what to look for and what your reactivity needs to be, so that way when things change, you can adjust to make sure that you're back in that performance window. Also, age of material. So most products have a 1-year shelf life on the ISO component and a 6-month window on the B-side component. There is a potential, depending upon storage conditions, that as that material ages, it may get slower. And what I mean by slower is the reactivity on a fresh drum and a reactivity on an old drum at the same temperatures could be different. So the older material may potentially need 5 or 10 degrees more pressure to get that initial initiation and take off. Not always the case, but this is something that we need to consider in the back of our mind. If I start my day off with a fresh drum and I tap into a 5-month-old drum and don't make changes, the foam's not going to be the same. All right, so it's us that needs to be aware of this. We need to be very experienced with our product and what it's doing, which goes back to documenting what you're doing throughout the day. If you're documenting reactivity speeds and you're documenting formulations, the more you do that, the more in tune you will get with that product and where it performs the best. But yeah, we have to get out of this mindset that it made foam, it sprayed, it stuck to the wall, it's good foam. that may be so, but there's performance points where it's gonna do the best. The better the foam performance, the better the finish quality, the lower your liability is. If we have a foam that's performing low on the board foot coverage rate, or maybe it's just a little bit more difficult to install, it's a little bit drippy, that also needs to be a correlation between possible liability down the road. Cold foam stinks, hot foam shrinks. All right, so if you're not making adjustments and you're just powering through it, you may have potential for things to go wrong after you leave. I've seen foam shrink a year later. I've seen odor complaints become a thing 5 years later. So remember, the better the performance of the foam, the less your liability is going to be. Air temperature. So air temperature is definitely probably the most item that you're going to have to pay attention to throughout the day. You're going to have multiple air changes per day, changes within the home. You know, if you're doing a basement, a crawl space, or a main level, and upstairs, and a base or an attic, you could have a 50-degree difference in temperature between the basement concrete wall and the roof deck that's got black shingles on it. If I get a daily log from somebody and it has one settings that's been made for the day, something went wrong. Whether you sprayed it too cold in the basement, you had it dialed in for the main floor, and it was too hot in the roof deck. So again, getting familiar with your product, playing with your product. You know, when you get a new product, make 20 adjustments a day. When you make an adjustment, give it 15, 20, 30 minutes to really level out and get settled before you make another one. But get your tech involved, give him your documentation that states everything you've done, allow him to help you get to kind of a mid-range number setting, and then you make the fine adjustments from there. Also, when you're using a weather app on your phone for like your humidity, your dew point, your temperatures, remember that is at a weather station, could be 10 miles away. Even if the weather station was right next door, the basement is going to have different environmental conditions than outside, and the attic is definitely going to have a different temperature, especially if it's retrofit with black shingles and sheetrock up. It could be 150 degrees in there. So what I recommend doing is one of the tools that are required, in my opinion, is a handheld weather station. That weather station needs to have 3 things: temperature, humidity, dew point. Dew point is extremely important. People don't realize how much water saturation in the air can affect the material. We're taking a hot, atomized material and passing it through air that can contain water. Well, water reacts with isocyanate. Water is part of the chemical compounds that we're using to make a polyurethane. If we're adding additional water because it's going through a saturated environment, we're changing the foam, right? So if we have documentation with humidity, dew point, and moisture content, we can probably see where things are going to go wrong. And the more we do this, oh, it's humid today, I'm going to have to add 5 degrees. Or, oh, it's got a lot of dew point, I may have to wait till about noon to start spraying because things are going to be weird. Dew point is one of the things I think most people look at and don't think about. Dew point is where you get on a job site and it's foggy outside. Fog is an indication of being at dew point. You have raw water droplets in the air. It is no longer a vapor. And the more you can pick up from point A to point B, the worse you're going to have an impact on your material. So sometimes even closing the distance between the gun and the substrate, you're going to pick up less material or less water. Pressures. One of the most important processing requirements is the energy inside the chamber where the impingement ports deliver the A and B components into the nozzle. Depending upon the viscosity, pressures will need to be adjusted to deliver the correct amount of energy to create efficient mix and pattern development. So throughout the day, we have experienced elevation changes potentially, right? So let's say we're on a multifamily residential construction site where we're at the first floor and maybe we go up to a 5th floor. If I don't adjust my pressures for that elevation, we are going to have different energy amounts at the impingement port. Right. Our machine will read, we're going to use round numbers. Let's say our machine reads 1,500 pounds. We pull the trigger, the needles drop to 1,200 pounds. We're making foam at 1,200 pounds. Well, if you're at ground level versus 50 feet, 60 feet in the air, your dynamic pressure, the energy being delivered to the impingement ports is going to be less because we are losing pressure, or we're gaining pressure at the machine, but we're losing pressure at the gun because we have to push that material up. It's got drag resistance as it's going through the hoses. Every time it makes a 90-degree turn, we're increasing drag, so where it goes over the railing can, have an impact. So again, you need to make modifications to your system to compensate for any of these impacts that you're going to be having. Depending upon the viscosity, the pressure will need to be adjusted in the amount of the energy created to affect the mix and the pattern. This goes for your closed cell guys. If you have a hose temperature of, let's say, 120 degrees, and you're in winter foam, you're getting too hot outside, so you start dropping your temperatures down on your system. You're at we're going to say we're at 105. This is the bottom of the processing bracket. You have increased the viscosity which that material is traveling through the hose. If you don't compensate with more pressure, you're going to lose energy at the impingement ports because that material is thicker. It's going to take more back pressure to push it at the same rate. So if you're going down in temperature, you need to go up in pressure, and vice versa. If you're going up in temperatures, you can potentially drop your pressures a little bit, so that way you're maybe not overspinning the product and you're making a halo pattern. You can do that. But be mindful, with viscosity, there are pressure adjustments. All right, so if you're cooling the temperatures down, you need to increase it with pressure. Every time I drop 5 degrees, I go up 50 PSI. The thinner the material in theory, the lower the pressure you can run it in suspense. Elevation will have a major impact on the energy at the gun due to pressure loss from gravity. Also, hose diameter and length can have massive impacts on pressures at the gun. So, perfect example, at the lab where we make our material, we run a proportioner with 50 feet of hose, 10-foot whip, and a gun. If I base my documents and processing parameters based on a 50-foot section of hose, and I tell you, 1,000 PSI, that's where you need to be. If I tell you that out in the field and you've got 410 feet of hose on an H40, yeah, that's not gonna work. All right, you're gonna have so much drag loss to the gun, you may no longer be at the point where there's enough energy at the impingement ports to create mix and spin the material to get a pattern. If you ever spray and your pattern's kind of small and it's got really large droplets and you can see it passing through the air, you may want to increase your pressures to get better mix, better spin, better atomization. Also, some machines allow for half-inch hose. So you may have a machine like an H40 that has 150 feet of half-inch diameter hose down to 3/8, down to 1/4 inch. That configuration is going to spray differently than a hose that's 410 feet of all 3/8. More drag, all right? So two machines, you can have a rig with two proportioners, one here and one here. This one has a 50-foot section, a half-inch. Your dynamic pressure settings are going to have to be different to have the same result at the gun. All right. Also, impingement ports can have a large impact on energy at the nozzle. It's extremely important to understand the difference between static pressures and dynamic pressures. I feel like I talk about this a lot. When I tell you I need you to set your machine for 1400 PSI and 120 degrees, some people think that they're going to go over to their machine, they're going to set it at 1400 degrees, or 1400 PSI and 120 degrees, and that's where they're making foam. That is not where you're making foam. The second you pull that trigger and you start flowing material through that system, your gauges are going to drop. Electric series machines are going to drop more than air series or hydraulic series, but there will be some cycling in those gauges. The lowest number achieved is where you made foam. So if you set your machine at 1500 PSI and you pull the trigger and they drop down to 1200 and they cycle, even though it might cycle back up to 1400, your dynamic pressure is 1200 PSI. That's where you made foam. I see a lot of these guys, especially these closed cell guys doing super high lifts, they'll bring their static pressure down to 1000 and then they'll spray because the pattern doesn't have a lot of energy and it's not tearing up the foam as it's rising. Well, 1000 PSI static, you're probably at like 600 dynamic. I don't know one manufacturer out here that says that 600 PSI is acceptable. And the reason we have these numbers is we know that we need a certain amount of energy introduction into that nozzle to get centrifugal force to spin these materials around the nozzle to get efficient mix. As that pressure drops, the two materials do not mix efficiently and you sacrifice your finished product. Yes, it's more controllable, I understand that. But what happens when your yield goes down, your efficiency goes down, your liability goes up. Because now you have potential for unreacted, unfinished polyurethane cross-linking inside that product, and now you could have odor. You could have all kinds of delamination. You could have cellular collapse. The foam just collapses on itself. This is something that's important, and this all boils down to learning your machine. I know that there's a lot of guys in here that are applicators, like myself, that we're on the gun, we can't see the machine. I highly recommend that one day, at least a week, let somebody spray a couple of cavities and just go stand in front of your machine, watch your gauges, see what's going on. Because I think you'll be surprised. You'll see that you set your heaters to 120 degrees. There are some machines out there at a certain flow rate, like with a 5252 or a 6060. You think you're getting 120 degrees, you pull the trigger, I've seen them drop down to 100 to 105. Now that material leaves your primaries, gets into the hose jacket, right? Well, once it gets into the hose, your hose might recover 5 degrees. That hose is not designed to heat your material up back to target, especially on 150, 200, 250 feet of hose. You might gain 5 degrees. That's it. So now you've got a sprayer that's material is up and down, it's hot, it's cold, it's inconsistent. You need to pay attention to the machine, right? And static versus dynamic is one of the biggest things I see us fail at, because we set the machine, it's in our mind that that's where we're spraying, and it's not. That's a baseline. All right. The pressures at the machine will be different than that is being delivered at the chamber from all of the above reasons. Machines can have major differences in static versus dynamic pressure from one unit to the next. I have personally built rigs where one machine was one number off the machine next to it. The hoses were the same, the whips were the same, the gun configurations was the same, and they sprayed different. The two machines did not spray the same. So as a company that has multiple rigs, that has multiple applicators, it's very important that the guy that's going to be spraying on that rig today understands that this machine is not like the other. It's going to take some time for him to realize that this machine maybe needs 200 more PSI. Maybe the hose reading, the temperature reading on one machine to the next is off by 5 to 10 degrees. Because as we have found over the years, I've been doing extremely deep investigations on consistency of hose heat from one unit to the next. You would be surprised on how many machines out there will say 120 degrees on the hose. I take that material out, I put it into a container, I measure the actual liquid temperature. I've seen 25, I've seen 30 degrees off. So you think you're spraying at 120, and you're really spraying at 100. The one next to you, the next machine, it might say 120, it might be 120. So in your mind, both machines are set up the same exact way, but one's gonna spray completely different. All right, so this brings me on to a topic of what we call hose heat checks or bucket checks. Anybody in here ever heard me say anything about a bucket check, right? So this is something that we've been doing over the years because I started seeing inconsistencies in our fleet. And what I recommend doing is anytime you add or subtract a section of hose becomes damaged or it needs repair, it just ages, or maybe once a month. Put your hose, set it out on the ground, spread it up, bring it up to target temperature, let it sit at target temperature for 10 to 15 minutes to level out. Discharge 1 gallon of A-side component into a clean container. Check that temperature with a mechanical device, whether it's a meat probe sensor. Just do not use infrared guns because a reflective surface will give you a false reading. So measure the fluid temperature and see how far off you are from your machine. Because if we don't do this, we're chasing a ghost every single day because we don't know what we're actually spraying at. We may get it, we spray it, we make some changes, it starts spraying nice. Now 30 minutes later, the material that's leaving the machine was accurate to begin with. Now we're too hot. Now that foam's changing again. Let's go back in there and we change everything, right? So this is why you have to get really, really in tune with your equipment and understand every piece of equipment is different. Any questions on that? No? Substrates, the types of substrates and their impact on reactivity is extremely important. Some properties can have multiple substrates in the same spray area. An example is a wood structure with a metal roof. There could be a potential of a 50-degree or more differential between the two sections of spray zone. Down here in Florida, we have block or precast exterior walls with timber frame trusses and OSB sheeted roofs. A lot of times we have clay, terracotta, or slate roofs, as well as dark shingles. If I'm spraying an exterior wall and I'm on my ladder spraying the tops, and I go from a 50-degree block wall to a 120-degree roof deck, do we spray the same foam? No. One of the two are going to take a sacrifice. I understand it from a perspective of production, that we're on our top, we're on our ladder, we're spraying the top of this 10-foot wall, but we got to knock out this roof deck. So a tip is spray hot on that concrete wall, because it's a heat sink, it's denser, it's probably getting a little bit thinner of a lift, 3.5 inches. You can manipulate your processing temperature with distance, okay? So you spray your wall close to keep the heat, and then when you spray your roof deck, get another 20 inches of distance on it. And what you're gonna do is you're gonna manipulate that process, or that mixed material, because it's traveling through the air, and now instead of setting your machines up 20 degrees cooler, you're taking heat away from it as it's traveling through the air. Does that make sense? All right. The biggest mistake we can make is go from a block wall 3-inch lift to a 6-inch lift on a hot substrate. Open cell, we've all seen it sprayed where it sprays hot and it collapses on itself, right? If it's doing that, back off, spray it a little more distance, see if you can do it. If it is such a severe difference and it's not working,